Thank you for joining us today. Please allow me to introduce Armando Solar-Lezama. Armando and his group have been working on a new class of learning techniques that combine symbolic and logical reasoning with deep learning in order to provide more interpretable models, better generalization, and improved data efficiency. In this presentation, Armando will share some of the group's recent work in this space and some of the applications they're exploring for this new class of learning techniques. Please feel free to send any questions for Armando to me in the chat, and I will ask on your behalf at the end of the presentation. And with that, Armando, please feel free to take it away.
Thank you. Thanks. And thank you, everybody, for joining today. So the plan is to talk a little bit about some of the work that my group has been doing around neurosymbolic program learning and its applications for improved machine learning. And kind of the high-level pitch around this is, we all know deep learning is great. There's a lot of really cool things that you can do with deep learning, but it also has some gaps around things where it sometimes falls short of what is needed for certain kinds of applications. For example, one big one is interpretability. You can often get very good black box predictions, but if you actually want to understand something about the mechanism for how something works, it might be less useful than something where you can actually have a model that you can probe and you can understand what is happening as part of that process. Data efficiency can also sometimes be a problem. Part of the philosophy behind deep learning is that you want to let the data speak for itself. And but if you want the data to speak for itself, you better have quite a bit of it. And there are some domains where data might actually be expensive or just not readily available. Another thing where deep learning is not great is in the way you can encode prior domain knowledge. Oftentimes, there are things you can do in the context of deep learning, for example, through data augmentation, to incorporate some of the domain knowledge that you have, but it's often in a way that is indirect. Finally, being able to distinguish between correlation and causation is something that is, in some applications, pretty important. And so where are we coming from for this? So it turns out that my group actually did not start out as a machine learning group in any way. My experience actually comes from the area of programming languages and formal methods. And it turns out that, less familiar to a lot of people, but there actually has been quite a revolution in those areas over the last decade or so, where our ability to reason about code and to reason about what programs are going to do has actually increased dramatically, to the point where automated bug finding, for example, which used to be niche even in the research community, is now very much an industrial tool, right? We have the ability to generate verified implementations of fairly complex pieces of code. We have the ability to really do logical reasoning at scale in order to analyze software and find bugs. And a lot of my own work has actually been focusing on leveraging these advances in formal methods for program synthesis. So the key premise of program synthesis is that you can take some information about the behavior of a piece of code that you want to generate. And this information might be in the form of input-output examples, might be in the form of just some safety properties that you want to be satisfied by the code. They can even be probabilistic information about this code. But the idea is that you can combine that with information about the structure of the code, how it should actually look like. This might be, here's the components that I know this code is going to have to use, or here's a skeleton of the program that I'm looking for. Or here's, again, even probabilistic information of some prior over the structure of programs that I care about. And the idea is that the program synthesizer can give you a piece of code that does what you want. And so this has actually been quite successful in a number of domains. For example, data structure manipulations, especially the kind of data structure manipulations for things like lists and trees. We can actually synthesize even verified versions of these pretty effectively nowadays. Data wrangling has been another domain where program synthesis has actually been quite effective. In fact, if you have a recent copy of Excel, there is a functionality called flash fill that allows you to take lines of text, transform the first one or the first couple of them in some way, and then the system under the covers will generalize that transformation into a program and use that to transform the rest of your data. And there actually has been a lot of work in the community around using program synthesis for doing data manipulation and data querying by example. And there's other domains, things like the kind of low-level, bit-level manipulations that you see, for example, in network protocols. We can synthesize them very, very effectively nowadays. And so now the question that you might be asking is, well, what does this have to do with machine learning at all, or with learning in general? So it turns out that if you look at this definition of the program synthesis problem, it actually shares a lot of relationships with the value proposition of machine learning, namely that I'm going to have some data that summarizes what this piece of code that I want is going to do. I have some information about my architecture, for example, and through some training process, I'm going to get a model that does exactly what I want. Now, so when we realized this, we realized that it might be possible to actually use program synthesis just out of the box for some applications that might not be so suitable for traditional machine learning. And in particular, these kind of applications where you have small amounts of data, where you really care about getting an interpretable model, and where you can get away even with relatively small models as long as those models are in the language that the people wanting to run this inference care about, right? So this was the first question that I started with. Could we use these program synthesis technology just directly for learning tasks? So for example, one of the projects that we started a few years ago, this was led by graduate student Kevin Ellis and was in collaboration with professors Josh Tenenbaum, also from CSAIL, as well as professor of linguistics, Timothy O'Donnell. And we were looking at this question of understanding language and understanding how language works. And in particular, we're looking at this problem of morpho-phonology. So at a very high level, if morphology, that's, for example, those are the rules in language that you use to come up with the past tense for a word. So for example, for the word open, the past tense is going to be opened, right? And there's a general rule in English that the way you create the past tense for a verb is that you put a D at the end, right? And this kind of rules vary from language to language. Every language has its own idiosyncratic rules and its own exceptions to those rules. Or in the case of phonology, for example, like the word walked, we know that this word is the past tense for walk, and you create that past tense by putting a D at the end. But notice that we say walked. We never say walked. It would sound weird if we said walked. And that's because there's a phonology rule that talks about when that D sound has to be translated into a more T-like sound. And by the way, if these characters look funny, it's not because my font broke. This is the kind of notation that linguists sometimes use to to define to write a word in terms of its sounds. So we have these rules, and these rules are different for different languages. And one of the questions we asked was, could we go to just a brand new language that we've never seen before, collect a corpus of words in that language, and then automatically learn from that collection of words the rules, the morpho-phonology rules for that language. And it turns out that this is a task that is actually very well suited for program synthesis. At some level, it is a learning task, right? We want to get some examples of these verbs being conjugated, for example, in a particular language. And then from those examples, we want to be able to generate a program that is going to do that translation, right? But at the same time, it has a lot of the features that made it that make deep learning not a very good choice for this. First of all, for some of these rarer languages, getting a giant corpus of words is going to be hard. We want something that works with a few dozen words and that generates that infers useful things from a few dozens of words rather than millions of words, or which might not even exist in that language. The other thing is we actually want to learn something about the structure of this language. It's not enough for the machine to understand what's going on. We want to understand how the language works and how these rules work. And ideally, we'd like to understand this in the context of the notation that linguists generally use to describe these sorts of things. And so rather than framing it as a traditional learning problem, we can frame it as a program synthesis problem. Now, it's a peculiar form of a program synthesis problem because the function that we want is a function that says, here's the stem of the word, and then we pass it through a set of rules, and then here's the form of the word and the meaning that associated with its meaning. The problem is we don't actually know what the stems of these words are. All we get to see is the output. We get to see how the words are actually pronounced in the language. But it turns out we can actually adapt our program synthesizer to do this, and we were able to come up with rules for all kinds of languages. I don't expect you to parse what we see in the slide, but suffices to say that what we have here are a set of rules written in the notation that linguists use to express this sort of thing that tell you exactly how you are going to generate from these unobserved stems particular forms of words. And we can learn these kinds of rules directly from data. And we've actually done this for a reasonably large collection of different languages. Our technique is more effective on some of these languages than on others, but it actually works much better than any prior approaches that have been tried. So this gave us a lot of excitement around the use of program synthesis for machine learning, and it seems to provide an opportunity, an opening to do something interesting. However, what we found very quickly was that the kind of program synthesis techniques that we are using also have a lot of shortcomings when it comes to some of these learning tasks. First, it's hard to scale them beyond small pieces of code. So things that you can represent, like in this more language example with small collections of rules, you can define, but things that require more complexity are difficult. And partly it's because you have, unlike deep learning, where you're relying on numerical optimization and automatic differentiation, in this case, we are searching very large combinatorial spaces of programs and of rules. And this is actually a very challenging combinatorial search problem. It's not able to leverage GPUs, for example, in the same way that deep learning is able to leverage these kind of hardware. And so by itself, we realized very quickly that it was not going to be the answer to our problems. And so more recently, what we've been studying is a synthesis of techniques, forgive the pun, of techniques from the programming languages and the formal methods side. A lot of these program synthesis techniques that work through logical reasoning, that are fully combinatorial, and machine learning techniques, which are based primarily on optimization, which tend to do a much better job at dealing with noise and uncertainty compared to the logic-based techniques coming from the programming languages community. And so recently, we've been studying different ways of combining these two different classes of techniques in order to take advantage, on the one hand, of the ability of program synthesis to come up with clean symbolic representations of the things that it learns, and its ability to learn to generalize from fairly small amounts of data by taking advantage of prior knowledge about the structure of the desired program, and combine that with the ability of deep learning to get to be able to both represent very complex distributions of complicated objects, as well as their ability to associate meaning with very unstructured objects. And so we've been exploring a few different architectures that combine these neural and symbolic components in interesting ways. So for example, one architecture and one approach that we've been studying is a pipeline approach, where essentially what you have is you start with a very informally stated goal, and you use deep learning to turn that informally stated goal into a very concrete plan, a concrete set of goals for a program synthesizer, which can then go and tackle these goals either in one shot or incrementally. And so you leverage the ability of the neural network to associate meaning with these sometimes ambiguous, highly unstructured objects. But at the same time, you leverage the ability of the program synthesizer to give you clean, structured representations of what you discovered. Another approach that has shown to be very, very promising is the neural guided search approach, where you want to leverage the ability of neural networks to learn complex distributions of complicated objects to essentially learn conditional distributions of programs, so that the neural network can look at your goals. It can look at what you're trying to do and help you craft a program that actually satisfies your goals. And so in this way, having a much more targeted search compared to what the more traditional synthesis techniques are doing. Another approach that we've studied that has also proven to be very powerful is the program extraction paradigm. The idea is that sometimes you have tasks for which you can actually train a neural network that will do exactly what you want and will do it reasonably well. But for some reason, for that task, you might prefer having something more structured, something that you can analyze, something that you can probe, something that you can audit. And so what you want to do is take that neural network and distill from that a more program-like representation, a representation that, that is more symbolic. But by doing it, by going through the neural network first, you gain a lot of the advantages of learning based on numerical optimization. And finally, the holy grail in this area, and we're definitely very far from this, is the ability to really learn just arbitrary combinations of neural and program-like components, right? Where you can actually synthesize programs that have program structure for many of the things where program structure is important, but also can leverage neural components that are learned in tandem with with the program. And so in the time that we have left, I just want to give a couple of examples of the ways in which we have used these different paradigms. And I want to focus in particular on the pipeline paradigm and the program extraction paradigm. And so for this pipeline paradigm, we actually had a project, and this project was also led by Kevin Ellis in collaboration with Daniel Ritchie and Josh Tenenbaum. I guess you're noticing a trend here in terms of our team of collaborators working on these problems. But the idea here was that we're looking at this problem of taking hand-drawn images, hand-drawn diagrams, and generalizing them in some way, right? So for example, here you have this grid and you want to turn it into a bigger grid. You want to clean it up and turn it into a bigger grid. Or you have this particular tree diagram and you want to clean it up and turn it into a bigger tree diagram, right? And so doing this kind of generalization is tricky if you're trying to do it exclusively in the neural domain. And it's also tricky if you're trying to do it exclusively in the program synthesis domain, right? Because generally program synthesis assumes that you have some very crisp specification that says this programs that satisfy this are going to be correct and programs that don't satisfy this are going to be wrong. But here we just have a picture, a drawing. It's hard for these logic-based synthesizers to do much with pictures. So the approach was to take this pipeline approach. So what we do is we start with hand-drawn images and we train a neural network to generate from the image a description of all the elements that are in the image, right? So this is a problem, for example, that is actually feasible to train even with a lot of synthetic data. We don't care too much about the distribution of how people draw these images. All we care is that we have some simple vision algorithm that is able to distinguish between circles and lines and that is able to tell us the coordinates of all these elements. And so what we get is from the image a description of all the elements in this image. And what's really powerful here is that now the neural network has taken us from the space of pixels to the space of symbols, right? And so now that becomes a reasonable goal for program synthesis, right? The goal of program synthesis is to come up with a program and a program structure that is able to match those elements that were observed by the neural network, right? And so now this is a problem that the program synthesizer can do. An interesting thing about this too is that the generalization happens not through the neural network, but it happens through the program synthesizer, right? When the program synthesizer discovers that these are loops of length 3, and so it's easy to switch those sizes so that now these are loops of length 4 or loops of length 10 if you want. And so in this case, the generalization is happening entirely in the symbolic realm. And what we find is that we're able to actually learn some fairly compact programs for many of these things. In many cases, the programs are significantly smaller than just the trace that describes what's in this image. And in that compression, what you get is generalization. What you get is higher level structure that allows you to generalize. And so here, for example, we can see a little gallery of some of the generalizations that we are able to get. You'll notice that some of these generalizations are absolutely spot on, and some of these are decidedly not. So for example, one generalization that is useful to highlight is here, where we see 2 lines emanating from the circle, and it generalizes to these lines that are not emanating from the circle at all. And part of this is because the way the generalization works in program synthesis, it's directly tied to your language. So for example, in this language, we have the ability to define lines emanating from particular coordinates, but we don't have the ability to define lines emanating from particular shapes. And so what that means is that the synthesizer is generalizing based on the position of the starting points of these lines rather than on the notion of the lines being attached to the circle, because in the language in which we're generating these, there is no notion of a line being attached to a circle. The language just says the line starts at this position, and it just so happens that there's a circle at that position as well. Another interesting feature is that the symbolic reasoning can actually make up for errors made by the neural network. So for example, in this example, the column in the middle represents what the neural network sees as the different elements in this shape, right? And so you can see that, for example, in the case in the top, the neural network is hallucinating an arrow that is not really there. If you squint, you can sort of see that, yeah, there is some part of this line that kind of looks like an arrow, and maybe it could be an arrow. In the case of the bottom, the neural network is hallucinating some triangles, and it's hallucinating some lines with slightly different coordinates. But once we go to program synthesis, we can actually let the synthesizer trade off faithfulness to the description generated by the network with simplicity of the program. And so the synthesizer can actually find that a program that doesn't involve this little arrow or that doesn't have a triangle, it's a much simpler program that much better leverages the regular patterns that the loop is able to create than a program that has to special case these things in order to get you these more complex shape. And so what we see here is this interplay between the neural and the symbolic in order to give you a different kind of generalization. Maybe this is a good point to ask for questions. And if there are any questions so far about the things that I've talked about.
Armando, yes, one question came in that was, does any of this work overlap with the tensor compiler work that Facebook was working on a few years back? Their approach seems analogous to the pipeline approach shown on slide 17, though they use an iterative evolutionary method.
So there is a whole space of work, for example, around the problem of AutoML that is very closely related to a lot of the work that we're doing here, where it's a little bit coming from the opposite direction. So it also has this combination of neural and symbolic, where you're searching this discrete space of neural architectures, for example. Genetic algorithms have actually been quite popular in this space precisely for their ability to deal with combinations of continuous and discrete, and helping find discrete structure. We have not used genetic algorithms as heavily in some of the domains where we have been able to do side-by-side comparisons between the symbolic search procedures that we specialized on and genetic algorithms. We have found the symbolic search procedures to be more effective, but the genetic algorithms have other advantages that can be useful, especially in cases where the scale of artifacts that you're searching for is much bigger than what the symbolic methods are able to handle.
Thank you. An additional question, are we beginning to see what this might mean in an enterprise context. For example, the relationship between code, data, and models is shifting in large-scale IT, such as digital process management.
So this is right now very much in the early stages. There are groups in industry, particularly Microsoft, Google, and Facebook, that are very active in this space, although it's still mostly within their research organizations. But there is a lot of interest within those spaces, especially when it comes to, for example, closing that circle, applying these techniques back to software engineering problems, where you want to learn something about code, but you want to take advantage of the fact that you have this ability to reason symbolically about the code as well. But I would say we're still in the very early stages of this technology.
Great, thank you, Armando. If you're welcome to continue. In the meantime, everyone feel free to continue to ask any questions in the chat.
Sure. So I want to give another example here, in this case about the program extraction paradigm, right? Because at some level, it might seem like, well, if you already have a function that does what you want, why would you want to now have a different function that may not even be as powerful as the one you learned in the first place, right? And so one domain where we have been exploring this is in the context of policies for multi-agent systems. So this has been work led by Jivana Enala with Yichen Yang and James Paulus and Evan Pu in collaboration with Osbert and Vijay and Martin Reinhardt and myself. So here, what we're looking at is the problem of controlling essentially a swarm of drones, right? So you can think of these as the problem of controlling a swarm of drones. And in this case, we're looking at pretty simple tasks. We have teams of drones that start in some position and want to move to a different position, right? Not that complicated. Can get a little bit more complicated if they have to avoid each other. And it can get pretty complicated if they have to coordinate, for example, to go to take turns going through a tunnel. And so this is a problem where if you have a very small number of these drones, you can just use traditional planning to just come up with a plan for every single drone and what trajectory they're going to follow. But that's hard to scale when you have really large or even moderately large numbers of drones in your swarm. And recently, people have observed that reinforcement learning can help with these tasks. And there has also been work looking in particular at the communication policies, right? And the communication policies that are used for each drone to send messages to other drones for letting them know what they're going to do or what they're going to be. And so in particular, a concrete architecture that you have here is that you have these agents, and at any moment, you can look at any pair of agents, agent I and agent J, and agent J is going to have a message policy where it's going to look at its observations, look at its state, and craft a message that it's going to send to to drone I. And drone I is going to have its own policy that is going to tell it who to pay attention to for these messages that are coming in, so that together this information can inform agent I of the action that it needs to take, right? And so this kind of approach has actually been successful in coordinating these teams of drones, but it has the problem. It has two problems. One is that the policy that you get is just this neural network. It might be a little inscrutable. Maybe you don't care about that, but it also has another problem that you end up with lots and lots of messages, and that's not so good from an energy efficiency perspective. And so our goal was to see whether we could take this neural network and from that neural network actually extract a policy that is defined in a higher level interpretable language, right? So we want to, again, our goal is not just to make sure that we can complete our task, but also to make sure that we minimize communication, both how many messages each individual agent is sending, as well as how many messages each individual agent has to pay attention to, right? And so what we find is that, for example, if you compare with a transformer network, you can actually visualize all the communication that is going on. And in this case, we're seeing the communication across different teams for one particular task. And what we find is that with our approach, by generating this custom domain-specific language and extracting from the transformer, extracting this domain-specific program, we can actually significantly reduce the communication, right? Rather than sending lots of information to everyone, we can really generate this sparse communication. And again, the other advantage is that you actually get an interpretable policy. So the language, the key to the language is that for every agent, what it's able to define is it's able to define a region. The way the policy looks like is that there's a region, and this region might either be just a flat region where the agent says, anybody within this region I want to communicate, or it might say randomly pick the another drone within that region. So the language that we synthesize actually has the ability to randomly select agents that satisfy a particular predicate. And or you can even impose a gradient that says, well, I want to give preferences to drones that score higher in this region. So one nice thing about this is that at any moment you can actually visualize how these regions look like and interpret what is the region that the agent is paying attention, where it's trying to select who to communicate. And so what we're able to see is that for these tasks that we started experimenting with, you actually see that the performance is comparable to the performance that you get with the transformer. So, for example, in this case, we're looking at loss, and especially so smaller is better. And you can see that our program-based policy, in most cases, it's fairly comparable to the transformer policy, especially in the scenario on the right, which is the more challenging scenario. But what we see here also is that the communication is significantly better for our program-based policies compared with what the transformer is doing. And so this really relies on this ability to take the neural network after it has been trained, and then leverage a program synthesis approach to discover these discrete this concrete program that is going to behave like the neural network. And so in doing this, we're able to go from a policy that incurs a lot of communication and that is completely opaque to a policy that that is actually more interpretable. So a little less than a year ago, we actually took this idea, and we actually launched a larger scale effort around it. So we have this project that is actually funded by NSF. It's through their Expeditions in Computing program, where we put together a team of researchers, both at CSEL as well as at several other institutions. And our goal is to continue pushing on the development of these neurosymbolic learning technologies, focusing in particular on the application of scientific discovery. The idea being that this is an application where some of the benefits of additional interpretability, for example, that you can get from these symbolic techniques, those benefits can actually be quite useful in understanding natural phenomena. For example, one of our new thrusts as part of this work is understanding RNA splicing, understanding how RNA inside our cells gets manipulated by this cellular machinery that is in charge of breaking it up and reassembling RNA before it's used to produce proteins. And this is an example where you could train a deep learning model to predict very accurately how a piece of RNA is going to be processed, the end-to-end. If you start with this piece of RNA, it's going to be processed into that piece of RNA. However, such a model is not particularly useful because it doesn't tell you how that process actually works. And so the ability to generate models that you can probe, that you can actually match against what is known in the literature and in the community about that process, means that you can move from simply making a prediction to truly understanding how a process works. And so I think this is a good place to ask for more questions.
Hey, Armando, yep. Prior to this NSF slide, one question: have you and your team explored using that approach to define an abstract, a finite configuration space to avoid collision?
So, not directly. One of the things that you get in some of these cases, especially when you have, for example, things that have to like pass through a tunnel and coordinate, is that the individual coordination is really important, and knowing exactly who to send a message to, so that, for example, they can take turns or align in a queue, is pretty important. So if I understand correctly, and maybe there's a follow-up here. So what you're asking is defining for different drones, kind of the regions where they move so that they don't collide with each other.
I'm going to see if they have a response. Um, Armando, that we'll go back to it via email. I just got
Sure.
another question. Could any of the techniques in the NSF project be used to understand engineered systems such as emergent behavior in infrastructure or social networks, or identifying hidden behavior, for example, cyber?
Yes, yes, absolutely. In fact, one of our thrusts as part of this project, and this is especially work that is being led by Michael Carbin, who is also part of our team, uh, has to do with understanding engineered systems. And so one example that Michael has been working on is just performance, right? Understanding performance and building performance models that on the one hand incorporate what we know about, say, how a processor actually works, but that also account for the fact that you have this emergent behavior and that it's very difficult to make accurate predictions, or it's just very expensive to make accurate predictions of performance based on detailed simulation. And so you want these models that, on the one hand, incorporate some of our background knowledge about performance, but also have the ability to let the data speak for itself and to allow us to capture some of these emergent behaviors.
Thank you. Another question, your work in optimizing communications with neurosymbolic transformers sounds like it could have applications in SMPC private deep learning. Example, Falcon. Have you considered applications in that area?
No, we haven't, and this is fairly recent. This is fairly recent work. Um, so this is actually going to that work is actually going to be presented in iClear. So it's very, very recent work, and if people have suggestions or pointers to potentially promising applications, we'd absolutely be interested in hearing about it.
Awesome. Thank you, Armando.
Mhm.
Those are all the questions we have right now. Do you have anything else you want to share with the group before we close out today?
No, I think I wanted to give people a bit of a sense of some of the techniques we have. We have primarily been focusing on applications to robotics, as well as the more program uh, software engineering type of applications. But I think this is really in the early stages, and I think there's a lot of potential for applications of these kinds of techniques into other domains.
Thank you so much, Armando, and thank you everyone for attending. I'll just say if any members that are watching this recording at a later date next week or next 2 weeks, please feel free to reach out with any questions, and I will connect you with Armando. With that, thank you so much, Armando, and thank you everyone for attending today.
Thank you. Thanks a lot.